navigating the sheer volume of information available today, especially, in fields like AI and machine learning that moves so fast.
Yeah.
It can really feel like just trying to keep your head above water sometimes.
Oh, absolutely. It's a deluge. And extracting those really actionable insights, the core knowledge, that's the major challenge.
Yeah, and while deep learning has been, well, incredible for perception tasks, think image recognition, language syntax.
Right, understanding patterns.
Exactly. But it often runs into limitations when you need deep knowledge representation and complex sort of multi-step reasoning.
That's precisely the gap, and that's where knowledge graphs, KGs, really come into play.
Okay, so KGs offer this structured way to model knowledge, right? Representing entities, things, concepts, and how they relate to each other, like in a graph.
Exactly. You've got those foundational examples like Freebase, Yago, WordNet, even NileL and DBpedia. They've been crucial for structuring all sorts of information.
They provide that symbolic structural backbone that deep learning sometimes lacks.
Making them, frankly, indispensable for tasks needing actual inference, real reasoning over interconnected facts.
And that brings us to our focus today. We're diving deep into a very active area, task-oriented knowledge graph reasoning, or KGR.
That's right. We're going to unpack the current state, look at its applications, future prospects, all drawing heavily from a pretty comprehensive recent survey paper on this topic.
So our mission here, for you listening, is to guide you through this material. We'll cut through some of the complexity, highlight the core ideas, the advancements.
Yeah, we'll explore what task-oriented KGR really is, how the techniques work across different scenarios, static graphs, dynamic ones.
Where it's being applied now,
Yeah.
and then look ahead at the challenges and the opportunities researchers are focused on.
And this deep dive, it's really tailored for you, our listeners, who are already pretty deep in ML, data science, math. We'll focus on the technical concepts from the survey, assuming you've got that solid grasp of the fundamentals.
Okay, so let's jump in. Before we get into the how do we even measure success? How do we evaluate KGR?
Right, evaluation is key. The standard approach, as laid out in the paper, is basically an information retrieval task.
Information retrieval. How so?
Well, imagine you're trying to predict a missing piece in a knowledge triple, say the object T in HR. The system generates a list of possible candidate entities for 2.
Okay.
Then the KGR model assigns a score, a likelihood, to each candidate, and you rank them based on those scores.
And the goal is simply to rank the correct answer as high as possible.
Precisely. Performance hinges on where that correct answer lands in the ranked list. The paper highlights 3 common metrics. First up is mean rank, MAR.
Mean rank. Just the average rank.
Yeah, simple average of the numerical rank of the correct answers across your test set. Lower is better, obviously. But the survey points out a weakness. MR is really sensitive to outliers, meaning if the model gets just one answer badly wrong, ranks it super low, that single bad rank can drastically inflate the overall average. Skews the picture.
Okay, so one terrible prediction messes up the whole MR score. Not ideal.
Not always. That's why mean reciprocal rank, or MRR, is very widely used. It's more robust.
Reciprocal rank. So 1 over the rank.
Exactly. Instead of averaging ranks 1, 2, 10, you average the reciprocals 11, 12, 1, 10. So a rank of 1 gives 1. A rank of 10 gives 0.1.
So lower ranks contribute much more to the average.
Precisely. A few very low ranks don't tank the score as badly as they would with MR. So higher MRR is better, and it gives a more stable picture.
Makes sense. And the third one hits at N.
Hits it in. This one's maybe the most intuitive. It's just the proportion, the percentage of correct answers that show up within the top N predicted candidates.
So hits at 1 is how often the correct answer was the very top prediction.
Exactly. And you often see hits at 3, hits at 10 as well. Higher hits at N is always better. It tells you how often the answer is nearby the top.
So the survey suggests MRR and hits at N are the go-to metrics, more reliable.
Generally, yes. They're considered more universal, provide a more balanced view than just mean rank. And one crucial detail for evaluation, you have to filter out any triples that already exist in your training or validation sets when you're generating candidates for testing.
To make sure you're actually predicting new knowledge, not just remembering old facts.
Exactly. It ensures validity. You're testing inference, not recall.
Okay, that evaluation framework seems solid, gives us a benchmark. Let's get into the techniques now, starting with what the paper calls static single-step KGR. Sounds foundational.
It is.
Yeah.
Static means the graph isn't changing. Single step means we're inferring direct, immediate links or associations, just one relation hop.
And the big player here is knowledge graph embedding, KGE.
Absolutely central. The core idea of KGE is transforming the symbolic stuff entities relations into numbers, specifically low-dimensional vectors or embeddings in some continuous space.
So you map the graph into a vector space.
Right, and once you have these embeddings, you can use math vector operations to estimate the plausibility of some potential new fact, like is this triple likely to be true?
So instead of symbolic logic, it's vector arithmetic determining truth.
Essentially, yes. It gives you huge advantages in scalability and efficiency, especially for massive KGs. You leverage fast numerical computation, but there's a trade-off, as the survey notes.
Which is?
You lose the explicit symbolic nature. The embeddings work, often very well, but they're kind of opaque. You lose that inherent explainability you get with symbolic rules.
That's a big one. Scalability versus explainability. What are the key types of KGE models discussed?
Well, the paper groups them. A really fundamental type is translation-based models. Trans-Z is the classic example.
Trans-Z, how does that work?
The intuition is surprisingly simple. A relation R acts like a translation vector. So for a true fact, HRT, the head entities embedding H plus the relations embedding R should end up close to the tail entities embedding T, like H plus RT.
Interesting. A spatial relationship in the embedding space. But KGs are graphs.
Yeah.
Surely graph neural networks are involved.
Oh, absolutely. GNN-based models are a major category. Things like RGCN, relation graph convolutional networks, they're designed explicitly to use the graph structure.
How do they leverage it?
They refine an entity's embedding by looking at its neighbors. They aggregate information from connected entities weighted by the relations connecting them. It's like passing messages along the graph edges to build context.
So the embeddings become aware of their local neighborhood in the graph.
Exactly. And there are extensions using attention mechanisms to focus on more relevant neighbors and so on.
The paper also mentions boosting KGE with extra information, like ontology.
Right. Many KGs don't just have facts, they have a conceptual layer. A ontology defining entity types, relation hierarchies, is links.
Like dog is a mammal is an animal.
Precisely. Ontology-enhanced models leverage this. One way is to jointly learn embeddings for both the fact layer and this ontology layer, using the hierarchy as constraints.
So it learns about dogs and mammals simultaneously.
Kind of, yes. It uses that structure. Another approach treats these concepts as entity types. It might guide entity embedding based on type, or learn separate type embeddings. Some advanced models, like AutoEater, even adjust type embeddings dynamically depending on the relation being considered.
Because the relevant type might change depending on the context, like whether you're asking about a dog's breed versus its diet.
Exactly. And then there's incorporating path information.
Right, multi-hop paths. They must contain richer semantics than direct links.
Definitely. Path-enhanced models try to capture that. They integrate information from sequences of relations connecting entities' multi-hop paths.
How do they encode paths?
Often using sequence models like RNNs or attention mechanisms over the path sequence. The goal is to bake the semantics of these indirect connections into the embeddings. Some recent work, like RPJE, even tries to bring back some explainability by integrating symbolic rules derived from these paths.
Trying to bridge that gap between embeddings and symbols again. The survey, mentioning open source libraries like OpenK, Ampagraph, Pykeen, that does suggest KGE is pretty mature now.
It does. It signals a well-established field with good tooling. But again, the paper reiterates that core limitation, interpretability. KGE results can be hard to explain, and they sometimes struggle with fine-grained semantic distinctions compared to logic.
Which leads us perfectly to the other side of the coin for static single-step, rule-based methods, designed for explainability.
Exactly. These methods focus on finding or using logical rules, often horn clauses, like if A and B, then C, directly from the KG data. They are inherently symbolic, offering transparency.
So more like traditional symbolic AI.
In a sense. The paper mentions two mainstreams. First, inductive logic programming, ILP. Systems like AMIE Plus are designed to automatically mine these horn rules by finding frequent patterns in the graph data.
Sounds powerful, but maybe computationally heavy.
That's the catch. ILP methods give you great explainability, grounded in logic, but they can struggle with complexity and scaling to truly massive KGs. Recent work focuses on optimizing queries or partitioning data to make it more feasible.
Okay, ILP is one stream. The other uses neural nets.
Correct. Models like NeuralLP, DROME, or the more recent RuleFormer use neural network architectures to learn rule-like patterns end-to-end.
How does that work?
They might integrate embeddings, use attention, or, like RuleFormer, even frame rule mining as a sequence-to-sequence task, learning to predict the rule consequence given the premise. It's an attempt to get rule-like reasoning with potentially better scalability from neural methods.
Trying to get the best of both worlds, explainability and scalability.
That's the aspiration, though their performance really depends on the quality and coverage of the rules they learn and how they aggregate evidence from multiple rules. So for static single step, you have this clear trade-off. KGE for scale and efficiency, rules for explainability.
Got it. Okay, that covers direct links. What about reasoning that requires traversing multiple steps, following chains of relations?
Right, that's multi-step static KGR. This is where you need to navigate paths, maybe multiple hops, to infer an answer.
Like finding a grandfather requires going parent, then parent again? Or complex dependencies?
Exactly. Traditionally, this involved explicit path-based methods. Think enhanced graph search algorithms, maybe a search like in a net, or using reinforcement learning.
Reinforcement learning, like an agent learning to walk the graph.
Yeah, models like DeepPath or Minerva train an agent to learn a policy for navigating the graph step by step, trying to find a path from the start entity to the likely answer entity.
Interesting. And the survey emphasizes large language models are making big waves here too.
Huge waves. LLMs are increasingly used, often in a no fine-tuning way, using them pretty much off the shelf.
How do LLMs do multi-step reasoning on a graph?
Well, often they don't directly traverse the graph structure in the way an RL agent might. Instead, methods might use the LLM to, say, extract relevant subgraphs, linearize parts of the graph into text prompts.
Turn graph snippets into text the LLM can read.
Exactly. Or frame the reasoning task as a question-answering problem. Give the LLM the question and relevant contextual graph facts as text, and let its internal reasoning capabilities figure out the multi-step connections. Models like StructGPT or Knowledge Navigator work along these lines.
So the LLM reasons over a textual representation of the graph data.
Often, yes, that's a common pattern. And significantly, the paper notes specific evaluation frameworks emerging for these LLM methods that don't just check the final answer, but try to assess the validity of the intermediate reasoning steps the LLM implicitly or explicitly generates.
That's crucial for trusting the output, understanding how it got there.
Yeah.
Okay, so far we've assumed the graph is static, but reality isn't static.
It definitely isn't. And that takes us to dynamic knowledge graph reasoning. This deals with KGs that change over time, facts get added, deleted, modified, or graphs that explicitly include time, often called temporal KGs or TKGs.
So the graph evolves or times the core dimension.
Correct. The survey highlights two main subtasks here. First, incremental KGE.
Updating embeddings on the fly.
Basically, yes. If your KG updates constantly, retraining a full KGE model each time is just too expensive. Incremental KGE aims to efficiently update the embeddings to reflect changes without starting from scratch. Different approaches. Some use multiple embedding spaces, others rely on continual learning techniques. The paper mentions methods like tie, which is notable for specifically handling deletions of facts, which is tricky. You need the model to forget outdated information.
That does sound challenging, learning, updating, and forgetting efficiently.
It's a balance. The second subtask is temporal KGR itself, reasoning over time.
So focusing on events with timestamps or durations, like subject, predicate, object, time.
Exactly. This is less about the graph structure changing moment to moment and more about understanding the temporal sequence, duration, and relationships between time-stamped facts within the graph.
How do models handle time?
Several ways. Temporal embedding models extend static KGE, incorporating time directly. T-Transy, Height, Tiro, ReNet are examples. They might make embeddings time-dependent or add time vectors into the scoring function. Some focus more on causal evolution between events over time.
And rules make a comeback for time too.
They do. Temporal rule learning methods discover logical rules that include temporal conditions. If A happens, then B happens within X time, then C will likely happen. There are also neural symbolic approaches like NuSys type, combining symbolic temporal rules with embeddings for accuracy and explainability.
Blending logic about time with neural pattern finding again. What about multi-step reasoning on these temporal graphs?
That's multi-step TKGR. It's about finding reasoning paths that respect temporal order or constraints. Imagine finding a sequence of events that logically and chronologically lead to some outcome.
So, pathfinding with a time dimension.
Right. Models often use RL to guide the path search, making sure the agent follows temporally valid steps, or use attention and GNNs to focus on temporally relevant neighbors when aggregating information. Cluster and TGT are examples here.
And LLMs for temporal reasoning.
Yes, LLMs are being applied here too. Approaches involve encoding sequences of time-stamped events and context for the LLM. Some rely purely on the LLM's reasoning over this temporal narrative.
Narrative, that's a good word for it.
Yeah. Others use hybrid models, maybe using LLMs to generate better textual descriptions of temporal events to feed into a temporal KGE model. Interestingly, the paper notes some LLMs like GPT-NeoX show emergent temporal reasoning capability just via in-context learning without explicit temporal fine-tuning.
Fascinating, just from seeing temporally ordered data. Okay, the survey also briefly mentions a few other key task categories.
Yeah, quickly. Multi-modal KGR, or MMKGR. This is about integrating info from different modalities, text, images, audio, alongside the graph structure. Think image-enhanced KGE or fusing text descriptions.
Bringing in richer data.
Then few-shot KGR. This tackles reasoning about rare relations or entities with very little training data, the long-tail problem. Often uses metric learning or meta-learning idea.
Learning to learn from few examples.
And finally, inductive KGR. This is crucial, reasoning about entities or relations the model never saw during training. It has to generalize based on subgraph structure, paths, or again, multimodal info linked to the unseen entity. Multimodal can really help here by providing richer signals for unseen things.
Okay, that covers the landscape of tasks and techniques pretty well. Let's pivot to applications. Where is all this KGR tech actually making a difference?
Good question. The paper points to several major impact areas. Question-answering systems are a huge one.
How does KGR help QA?
It lets QA systems go way beyond simple keyword matching or fact lookup. KGE can find relevant facts, but multi-step KGR is essential for complex questions needing inference across multiple KG facts. It helps understand the relationships needed to find or derive the answer. Plus, integrating causal or structural KG info boosts accuracy and explainability.
Explainability again. That seems key for recommendations too.
Absolutely critical for recommendation systems. KGR improves accuracy by finding subtle user-item connections, but maybe even more importantly, it enables explainable recommendations.
How so?
By finding the reasoning path in the KG connecting a user's profile or history to a suggested item, the system can say why it's recommending something. We recommend this because you like that, which is related via this path. That builds massive user trust. Models like KPRN or Cogger focus on this.
Right, moving beyond people who bought this also bought.
Yeah.
What about vision?
Visual reasoning, especially visual QA. Often, answering questions about an image requires knowledge outside the image pixels, common sense knowledge, domain knowledge.
Like asking, what is the cat likely to do next?
Exactly. KGR can link objects or actions identified in the image to a KG, and then reason over that graph to answer the question using external knowledge. FVQA is a key dataset here, and models like Graphhopper combine visual scene graphs with KGs.
Grounding vision in structured knowledge. The survey also mentions broad impact in vertical domains.
Yeah, it really highlights the breadth. Healthcare drug interaction prediction, diagnosis support, business sophisticated recommendations, risk modeling, education personalized learning, transportation using spatiotemporal KGs for traffic or passenger flow prediction, environmental science, social science. It shows KGR is becoming a foundational enabling technology across many fields.
That's quite a range. So wrapping up, let's look at the future. What are the big challenges and opportunities the survey identifies?
Several key challenges related to the nature of KGs themselves. One is sparse KGR. Real KGs are often sparse. Many entities have few connections. This makes it hard for methods like KGE to learn good representations.
Not enough data per entity.
Pretty much. So research looks at using rules or fusing external text knowledge, like with BERT-conv, to help enrich sparse areas.
And knowledge isn't always black and white, right? Uncertainty.
Right. Uncertain KGR is about handling facts that aren't definitively true or false, but have probabilities or degrees of belief. This needs representations beyond simple vectors, maybe using Gaussian distributions or specialized embeddings like in KG2E or BEER. The challenge isn't just representing uncertainty, but propagating it correctly during reasoning.
And errors. KGs must have errors.
Oh, definitely. Especially automatically constructed ones. KG error detection is vital, finding noisy or just plain wrong facts. This is tough. Approaches use rules or KGE-based anomaly detection to flag suspicious triples, but reliable ground truth for errors is scarce, making it hard to evaluate detection methods.
So dealing with sparsity, uncertainty, and noise in the KG itself are big hurdles. What about the big opportunities?
The survey really points to the integration of KGR with large language models as the major research hotspot. Think LLM-enhanced KGR, or XE as some call it.
How do they help each other?
It's seen as synergistic. LLMs can boost KGR by using their language skills to retrieve relevant text, expand descriptions for KG entities, help interpret relations, maybe even aid in KG construction.
And KGs help LLMs.
Yes, by providing structured, factual, verifiable knowledge. KGs can help ground LLM outputs, reduce hallucination, and potentially bring much-needed structure and explainability to the often opaque reasoning processes within LLMs.
So finding that perfect blend of symbolic structure and subsymbolic power.
That's the core research direction, how to best combine KG structure and reasoning with the flexible, powerful, but sometimes ungrounded reasoning of LLMs to build truly robust, trustworthy AI.
Okay, so let's synthesize. Key takeaways from this deep dive. Task-oriented KGR is vital for pushing AI toward more complex, knowledge-driven tasks, moving beyond just perception.
Absolutely. And we've seen a really diverse landscape of approaches: static, dynamic, multimodal, few-shot, inductive, powered by techniques like KGE, rule learning, GNNs, RL, and now, increasingly, LLMs.
These methods are driving real progress in applications from QA and recommendations to very specialized domains like healthcare and transport.
Definitely making an impact. But, as the survey emphasizes, significant challenges remain around KG sparsity, uncertainty, and data quality.
Which leads us right to that final provocative thought stemming from the survey's look ahead. As KGR and LLMs continue to converge, how do we effectively bridge their fundamental differences? How do we architect systems that truly harness the explainable structure of KGs and the powerful, flexible reasoning of LLMs?
How do we combine their strengths to create that next generation of AI agents capable of truly robust, knowledge-grounded, and explainable reasoning? That's the big question shaping the field right now.
A lot for us, and for you listening, to think about as this area continues its rapid evolution.